Namaste friends, my name is Amit Rajendra Kathare. I am a student of Computer Science and Engineering from Ramdeobaba University, Nagpur. Today I am going to teach you the Deutsch Algorithm from the subject Quantum Computing. So let's get started. The Deutsch Algorithm is one of the earliest and the simplest examples in quantum computing that demonstrates how a quantum computer can outperform a classical one. This was developed by physicist David Deutsch in 1985. This algorithm addresses a basic but important problem and offers a glimpse into quantum speedup. Though it may seem trivial, it has paved the way for more advanced algorithms such as Deutsch and Grover's and Shor's algorithm. So let's see the problem statement. The problem statement is such as we have given a function that goes from 0, 1 to 0, 1, and we have to determine whether it is constant or balanced. So the function is a black box function. The black box function is a function in which we can't see what is happening inside a function, but we have only information about the input and output. So our goal is to determine whether f is a constant or balanced function. We can solve this by two ways, a classical approach and a quantum approach. So let's move further. So let's get started with classical approach. The classical approach suggests that check both f of 0 and f of 1 to answer this. So it requires to evaluate f of 0 and f of 1, and we can only conclude after evaluating both the results. So it may require two queries. So let's go for quantum approach. The quantum approach states that we don't have to evaluate for two times, but we will evaluate in once by taking the both in superposition. This concept is called as quantum parallelism. We can evaluate both f of 0 and f of 1 at the same time using a single function call. This is achieved by preparing the qubits in superposition, allowing the computer system to explore multiple possibilities simultaneously. So let's see what are the steps and setup towards the algorithm. The setup and steps towards the algorithm. So let's initialize two qubits, that is qubit x equal to 0 and qubit y equal to 1. And let's apply Hadamard gates to the both qubits. Now apply the oracle UF, that is our black box function. Now next apply Hadamard to the first qubit only and measure the first qubit. So we will get answer as if the result is 0 then the function is constant, and if the result is 1 then the function is balanced. Let's see the circuit diagram. This is our circuit diagram in which we can see that this is the quantum circuit diagram representing the Deutsch algorithm. As we can see that it includes Hadamard gates on the both qubits, the oracle UF in the center, that is our black box function, and the measurement at the end. This visual representation helps us understand how the algorithm operates at quantum level. Now let's break down the circuit diagram of the Deutsch algorithm step by step towards the evaluation of the quantum states. Let's get started with the circuit diagram explanation. We have qubit psi 0, that is equal to psi qubit 0 0. This means both qubits are initialized to 0. Next, we apply the x gate on the second qubit, converting it into gate 1. The state now becomes psi 1 equal to gate 0 1. This steps set the auxiliary qubit to the gate 1 state, which is essential for the function evaluation. Now we apply Hadamard gate to the both qubits. The Hadamard gate creates a superposition. The resulting state is psi 2 equal to 1 by root 2 ket 0 minus ket minus plus ket 1 and ket minus, or compactly psi 2 ket equal to ket plus and with the tensor product of ket minus, as we can see here. Okay, this is the key step that enables quantum parallelism. Both input values 0 and 1 are now being processed simultaneously. Next, we apply the oracle, which encodes the function f of x into the quantum state. The oracle transformation modifies the phase based on the function value. If the function is constant, that is f of 0 is equal to f of 1, the resulting states become ket psi 3 equal to plus or minus 1 by root through ket 0 plus ket 1. This occurs whether f of 0 is equal to f of 1 equal to 0 or f of 0 equal to f of 1 equal to 1. However, if the function is balanced, that f of 0 is not equal to f of 1, then the state becomes ket psi 3 equal to plus or minus 1 by root 2 ket 0 minus ket 1. Here the oracle introduces a relative phase between the basis states, which is the quantum signature of a balanced function. This concludes the transformation stage in circuit. In the next step, we will apply another Hadamard gate and measure the first qubit to determine whether the function is constant or balanced. So let's move further. Now we will see the constant sets for constant and balanced function. Now let's look at how quantum states behave differently when dealing with constant and balanced function in Deutsch algorithm. Case 1, constant function. In this case, if the function outputs the same value for both inputs, meaning f of 0 equal to f of 1, after applying the quantum gates, the intermediate state psi 3 becomes a superposition of ket 0 and ket 1 with a positive sign. This is denotes as the plus state or ket plus, as you can see here. Now, before measurement, the final states collapse to ket 0, so we know the function was constant. Now the case 2 is of balanced state. Now if the function is balanced, meaning f of 0 is not equal to f of 1, the quantum interface works differently. The intermediate state psi 3 now become the minus state or ket minus, which is difference of ket 0 and ket 1. After running through the circuit, the final state collapses to the ket 1, indicating the function is balanced. So by simply measuring the output, we can determine if the function is constant or balanced with just one evaluation. That's the power of the Deutsch algorithm. Now let's see the result interpretation. The result interpretation says that if we measure 0, then the function is constant since f of 0 will be equal to f of 1. And if we measure 1, then the function is balanced since f of 0 is not equal to f of 1. So let's see it through the table. Okay, when f of 0 is equal to 0 and f of 1 is equal to also 0 and type is constant, then the output we will get is 0. And next, when f of 0 is 1 and f of 1 is also 1, type is constant, then output will be 0. When f of 0 is 0, f of 1 is 1 and type is balanced, then output is 1. And last but not the least, f of 0 is 0, f of 1 is 0 and type is balanced, then output will be 1. So let's see why it matters. Why it matters. This is the first step towards the real quantum advantage. It is the foundation for Deutsch algorithm, Grover's algorithm and Shor's algorithm. Shows the power of quantum interference and superposition. Though it is simple, it laid the groundwork for more powerful quantum algorithm. It also introduced core quantum principles like interference, entanglement, and superposition, which are used extensively in advanced algorithms. So let's move to the end part, that is our conclusion. Conclusion says that to summarize the Deutsch algorithm, it is conceptually simple but revolutionary technique. It shows that even basic problem can benefit from quantum solutions. More importantly, it proves that quantum computers have the potential to outperform classical computers for certain tasks. Understanding this algorithm, it is essential for anyone studying quantum computing. Now, I would like to thank everyone who supported me in this whole video preparation, especially Mr. P.D. Bensare sir, who is my professor for the physics. And now I would like to conclude video here. Thank you.